Hi viewers, this is Dr. Gunamani Jana and you are watching video with me on nature inspired computing techniques. In this series, today we will be discussing about the ant colony optimization algorithm or the ACO. The outline of our presentations is the ant colony optimizations, the history and main idea, what is the ACO concept, what are the characteristics of ACO, the basic steps of the ACO algorithm, the applications of the ACO algorithm and some of the references will be covering. So while we are covering this history of this ant colony optimization algorithm, this ant system was originally developed by Marco D'Arrigo of Italy in the year 1992 in his PhD thesis. And the Max-Min ant system is developed by Huss and Stossel in the year 1996, 4 years after that one. And the actual ant colony, it was developed by Gambardella D'Arrigo in 1997. So 5 years after the PhD thesis, it was submitted in 1992. In the year 1997, this ant colony optimization was developed. So it is a probabilistic techniques to solve optimization problem, and it is a population based meta heuristic used to find approximate solutions to an optimization problem. And the optimization problem must be written in the form of a pathfinding with a weighted graph. So this is the idea. From a small diagram you can see the ants go from the nest to the food, that is the global waste, the food. So they follow various paths and they finally select the shortest path. You can see the diagram here. This is the nest and this is the food. So there are a number of paths from this one to this one, and finally the ant find the shortest path. The way ants find their food in shortest path is very interesting, and ants hide something like the pheromones. This is some chemical to remember their path. So these pheromones evaporate with time. So if it is exposed to longer time, the smell it evaporates. And whenever an ant finds food, it makes its return journey with pheromones. Okay. So and pheromones evaporate faster in longer distance or the longer paths. So this is the principle we are following. Then this ACO mainly we are using for the shortest path and routing. This is for assignment of the problems and also set problem. All the things we use this ACO, okay, or ant colony optimizations. And this ant will move from node I to j with a probability that is represented by the probability of ij, which is of tau of ij alpha, neta of ij beta, divided by summation of tau of ij alpha and neta of ij beta. So let us have what is the terminology. Tau of ij, it is the amount of pheromones, the age between I and j, what is the pheromones, that is the chemical ejected by these ants, that is the represented tau of ij. Then alpha is a parameter to control the influence of this tau ij. Then neta ij is the desirability of age ij, typically 1 by d of ij, and beta is the parameter to control the influence of this neta ij. So these are the things, the probability that a ant will move from one node I to another node j, that is represented by this one. Then the amount of pheromones is updated according to the equations. So tau of ij, which is equal to 1 minus rho into tau of ij plus delta tau of ij. So this tau of ij, as I told you, that is the amount of pheromones on a given age I and j. Rho is the rate of pheromone evaporations, and delta of tau ij is the amount of pheromones deposited, and this is typically given by this equation delta of tau ij k, that is if ant k travels on the aij, then it is 1 by L of k, other cases it is 0. Okay. So this L of k is the cost of the kth ant's tour, typically the length, right. Then okay, this equations are enough. So let us see how actually it happens. Suppose this is the nest, see the figure number 1, this is the nest and this is the food or the goal. and initially one ant, it starts here, it is going in this direction, leaving the pheromones. Okay. Then after some times some other ant also they are following, here they are going. Okay. And they go on traveling in this way, and they see the timing and everything, and after certain times you will see they are all aligned to the shortest path here. They will discard this path and they will discard this path. So this is the technology we have to learn from them and apply for the shortest path. Fine. Now these ant algorithms were inspired by the observation of real ant colonies. Ants are social insects that live in colonies and whose behavior is directed more to the survival of the colony as a whole than to that of a single individual components of the colony. That means the colony, the living in the colony, that is more important. Social insects have captured the attention of many scientists because of the high structurations level their colonies can achieve, especially when compared to the relative simplicity of these colonies individuals. So instead of individual, they give stress on this colony. So protection of this colony for food and everything, it is a priority. So an important and interesting behavior of the ant colony is there, foraging behavior, and in particular how ants can find shortest path between food sources and their nest. Ants are capable of finding the shortest path from food source to the nest or the vice versa by spelling pheromones, which are chemical substances they leave on the ground while walking. And each ant probabilistically prefers to follow a direction rich in pheromones. As I told you that suppose a ant is following a longer distance, so there is the chance that it will evaporate, the smell will evaporate. That means the other ant cannot follow because the pheromone is not there. But wherever a pheromone or the smell is existing, they will prefer to, because they understand the previous ant followed the same route. So this behavior of real ants can be used to explain how they can find a shortest path. The main idea is that it is indirect local communications among the individuals of a population of artificial ants, and the core of the ants' behavior is the communication between the ants by means of chemical pheromones trails, which enables them to find the shortest paths between their nest to the food structures or the food sources. This behavior of the real ant colonies is exploited to solve optimization problem. The first step consists of many on the initialization of the pheromones trails at the beginning, and each ant builds a complete solutions to the problem according to a probabilistic state transition rules. They depend only on the state of the pheromones. You see the step 1, we initialize the pheromone trails. So there are so many paths are there based on these pheromones, so but we find the shortest one. Then you go for the iterations, step 2, then repeat for each ant, solution construct using the pheromone trail, update the pheromone trails until stopping criteria. Okay. So this is the idea, main idea. Then let us see the ACO concept, how it works. The ants navigate from nest to the food sources, and you will be astonished the ants are blind. And the shortest path is discovered via pheromone trails, and each ant moves at random, and pheromones is deposited on the path. More pheromones on path increases the probability of path being followed. That means if the path is short, then more frequency the ants follow or the travel. So there is the more probability that pheromone or the smell will be there. So this is the basic concept of the ant colony optimizations. Now let us have a idea in details. So you observe this figure number 1 here. 2 ants start with equal probability of going to the, so this is the nest and this is the food. So here one started, here also an ant started. The moment the ant 1 reach here, the ant 2 is still going there. Second, now they have to return because they found the food. This will immediately return, and then after reaching it will return. The moment the first ant reaches here, you see the second one, then it is still, it reached here and still roaming. Still it is roaming here. Okay. The ant on shorter path has a stronger 2 ant from time to its nest to the food. So you can see here immediately the ant which has traced the food, it has reached here. The density of pheromones on the shorter path is high because 2 passes by the ant as compared to 1 pass. Here only one time it has passed, still it is in the middle. Here 2 times passed. So the next ant will, while it is moving here, he will have a strong smell here instead of here. Okay. Then the 2 or 3 ants are going, because by this time these pheromones it will be evaporated, and the moment it reaches here, so many ants moving in this direction, and you can see, and finally they will follow the routes instead of following this route. Okay. The next ant takes the shorter route, and like that all this iteration takes place. From this diagram you can clearly understand how they find the shortest path and what is the principle based on that it is worked. Okay. Then we see the flow chart. We start, then initialize the parameters, generate global random, calculate the fitness, update the pheromones, apply transition, then find the next one. See, if he in the iteration go for the number of iterations, if it is no, then again you go for the generating the global random. If it is yes, end it. So, okay. So this is the flow chart. Then we go for the basic steps of the ACO algorithm. So here you can see in this figure, pheromones update phases is located after the initialization phase, means that quantity of pheromones intensifies at each iterations with the reduced search space. Thus global optimization. Okay, so all the explanation it is given it here. So here for I is equal to 1 to I, maximum I 1 to I. So I the cycle number of cycles. Okay. If I is equal to 1, then generate m random ants within the FSS. Else, so FSS it is given in the feasible search space FSS it is given here. You can check it here, the feasible search space FSS. Okay. Now what I am telling, if I is equal to 1, then generate m random ants with the FSS in that feasible search space. Else reduce FSS with the range. So this is the equation. So we can reduce using that one. Here using some best and the beta one parameter we are using it here. Okay. Okay. So constant. So and if for I is equal to 1 to m, determine f of, this is the function we try to find it out there, that is the fitness function. Then save of xt of best, and then what is the pheromone update, pheromone evaporations, evaporate pheromone and trail, so all the things, and the solution phase determines search direction, generate the values of this alphabet. So all these things it is explained, you can clearly understand. And the number of ants being associated with m random initiatives like x to the power k is equal to 1 to m. Okay. Then xt of k new, which is equal to xt of k old plus minus alpha. Okay. So this alpha it is again one constant. So and alpha is the vector generated by randomly determining the length of this jump. Okay. All the things it is explained here, I think you will find. Then x of t best, which is equal to x of t best plus. So this is 0.01. This is the value it is already given, the beta value. So now using all the things we can calculate this algorithm. Just you go through this algorithm, and this ACO uses the real numbers instead of coding them as in genetic algorithm to optimize any given objective functions. This is one of the main advantages of the ACO, that it provides to optimize the signal timing with less mathematically all the things, right. Then this ACO uses the real number instead of coding them as an GA genetic algorithm to optimize any given objective functions. This is one of the main advantages of the ant colony optimization, that it provides to optimize the signal timings with less mathematically lengthy. Then moreover, Across algorithm has the ability to reach to the global optimum quickly without being trapped in the local optimum because it uses the reduced search spaces and the values of the optimal time bases are you understand, because the ant try to follow the least path because of the pheromones, the smell, and the accuracies reach to the global optimum or near global optimum as ants find their routes to the limited space. Fine. So there are some advantages and disadvantages of this algorithm. What is the advantages? It is simple for implementations, easily parallelized for concurrent processing. The derivative, there is no derivative. That is efficient for traveling salesmen and similar problems. Disadvantage is that probability distribution changes by iterations and time to convergence is more. Okay, is uncertain. Okay, convergence time is more, but convergence is guaranteed. Okay, solution is guaranteed. Then some of the applications we can see it here. routing in telecommunication network, traveling salesman problem, graph coloring, scheduling, constant satisfaction. These are the some of the things, and you can see some of the references here and collinear optimizations by Marco Dorigo, the main person who has developed a lot of things here. Then you can see 1 to 5, all the 5 references, and 6, 7, 8 also there. These are the some of the papers which is published. So thank you for watching this video. If you like this video, please do share with your friends, and also don't forget to subscribe to directly get the new videos. And have a good day, and please take care of your health. If any queries and anything, please be free to email me in this email ID or in this website. Thank you a lot.